Hello, let's talk about some of the stuff we're going to need out of chapter 26 here, mainly dealing with current and resistance. Starting with some basic definitions. Current is going to be the rate of charge flows, it's the rate at which charge moves. You can tie this back to, if you want a microscopic view, you can relate it to the velocity of electrons or charge carriers in your material. But for us, we're going to have a basic kind of calculus-based definition here. Whenever we see a derivative, derivatives always tend to mean derivate. That's not what I'm going for. Derivative. Basically, always means that we're talking about rate. So dq dt is the change of charge with respect to time. We're never really going to need to talk about this as a derivative, but calc-based course, let's put a definition on the table that makes sense. We're also going to want to talk about resistance, which is the characteristics of a conductor. It has to be a conductor or else charge just isn't moving. To impede current or to resist current, hence why the term is there. So let's take a look at this for a second. R equals V over I, so it's the ratio of the voltage to the current. So if you have a low resistance, so if R is low, that means that this ratio is low, which means that the current, for fixed voltage I should say, means that the current is high. Another way of looking at this, you phrase this in terms of Ohm's law, which basically says that the voltage is the current is proportional to the voltage, or the voltage is proportional to the current is how I phrased it here, I guess. And so for a fixed voltage, if you have a low resistance, you have a high current. If you have a high resistance, you have a low current. So the slope of a voltage current graph would then be your resistance. This is, I should specify, if ohmic. Realistically, you're probably gonna see like this do some weird spiking stuff, and maybe down here it's a little curvy. So this is what we would consider then not ohmic. Realistically, this is, an ohmic resistor is an ideal resistor, something where this relationship is linear. There's no weird complication. We will almost always take this as our model, although you may want to verify that when you're dealing with a resistive element, that it is in fact ohmic. That's an assumption that you are making. It's best to try to justify it. Alright, so Ohm's law, useful thing. Now the question we got to kind of address at this point, where on earth are we getting this whole resistance from? And so resistivity is going to be a material property that gives rise to resistance. So a simple model we have is that the resistance of a conductor is proportional to the resistivity. So that makes sense. If it's a more resistive material, whatever you've made out of it will have a greater resistance. It is linear in the length of the material, and it is inversely proportional to the cross-sectional area of the material. So you can imagine if you have a pipe is a simple matter for this. The more kind of resistive the pipe is somehow, the harder it is to push material through it. The bigger the pipe is, the easier it is to push material through it. So this would be hard to move through. This would be easy. So as A goes up, the resistance goes down. And the greater the patch of resistive pipe, the greater the length of it, it's just getting harder as this gets longer. So this is a simple model that holds for cases where you have a homogeneous material. You're not like mixing stuff up, get anything weird. It's isotropic, so the orientation of it doesn't matter. And you've connected a voltage basically so that I have a block of material. I have this whole thing is at one potential and this whole thing is at one potential, as opposed to just putting like point things. So points, you get weird field lines that have curvy stuff, things that we don't need to really worry about. If it is just parallel plates, the field lines go all the way across. The larger the piece of material, though, the less this region where it's weird is going to matter. So this is the weird region. So for a sufficiently large conductor, the difference between these two things is slight. All right, so we have an idea of current, we have an idea of resistance. These are the basic terms we're going to use to kind of start talking about circuits. We have an idea of where resistance comes from a model basis. The last thing we want to talk about is this idea of power. Power is going to be the rate of transfer of energy. So it's going to be, again, the derivative of energy, dE dt. Specifically, we're looking at the rate at which electric energy is transferred. And so we had said that we could define electric energy in terms of this idea of a potential. Remember we said that UE was equal to VQ, or that the voltage is the energy per charge, basically. Now, for a scenario where I have a constant voltage, then the voltage doesn't, this derivative, this rate thing, it's just a constant compared to that. So it can come out of the derivative, and that's what we see down here. And so we're left with dQ dt, which we remember, dQ dt is our current. So here's our expression for the power delivered by any element in a circuit. It is the voltage across the element times the current in that element. So voltage across element, current in element. And so kind of a way to think about this in terms of the analogy we were making between this and gravity, we're saying the power delivered is more or less the height of the element times the rate at which you are pushing masses through that height, if that makes sense, or up that height. This is the voltage is saying what the difference in height is, what the difference in voltage is between the 2 points of this element. And then the current is basically telling you how many charges, or how much mass in the gravity case, you're pushing through it, at what rate you're doing that. So that's what's going to tell you ultimately about what power you're delivering. Now, for the case of, specifically for the case of a resistor, from Ohm's law we know that V is equal to IR. So we can say that this is, for a resistor, that power is equal to I squared R. Alternatively, we could say that, I is equal to V over R. So this could also be V squared over R. Also resistor. All right. Our major concern in this unit is basically discussing simple circuit elements, not in a circuit fully yet, but basically talking about the relationship between voltage and current for a given element. So, getting this idea of resistance and being able to talk about where this idea of resistance is coming from as a material property. This should give you enough to get you started looking at the homework. Good luck. Let me know if you have questions.